Hello, how's it going? So, yeah, we're starting the next section. In fact, this is Chapter 2, Section 1 in the Larson book. And we're going to talk about the tangent line problem, which is to, in the first example, we have a function, f of x equals x squared plus x. And we want to find the slope of the tangent line to the graph of the function at the point 1, 2. Right? So where x is 1 and y is 2. So here's the graph in green on the right. And at the point x equals 1, you can see right about here in red, there's y equals 2. So it's very tiny, but here's 1, 2. And so at that point, there should be a line that just touches the graph but doesn't cross it. So it should look something like this. Right, so pretend it's a straight line. And we want to find the slope of that line, right? So we want, rise over run. So slope, which we'll use m for slope, right? Again, informally, we can think of it as rise over run, or specifically y2 minus, y1 over x2 minus x1. Right? So that's the definition of slope, right? So you should know that. However, notice that the only point we have on the graph here is the point 1, 2. Right? We don't really know where the x-intercept is. We don't know where the y-intercept is. Although you can see it looks like 0, negative 1 here. Notice how sloppy my graph is. I might be wrong. It might be, right, the y-intercept might actually be down here at negative 2 or at negative 1.5, right? So I really don't know. In fact, it is kind of sloppy here, so it's really hard to tell. The only point we know for sure that's on this line, right, at this point, is the point 1, 2. X equals 1, y equals 2. Okay? So based on that, whether you call that x1, y1 or x2, y2, doesn't really matter because, x1, y1, right? Or x2, y2, if it's all the same point, you see what happens, right? The difference in the y's over the difference in the x's, you just get 0 over 0, which, if you remember, is indeterminate. So that can't be the slope, right? It's not 0 over 0, as we've talked about many times. Okay, so what do we do, right? Well, we're going to have to look at other points on the graph, right? Not the graph of the line, the graph of the function x squared plus x, right? So if I take this and sort of blow it up down here, we have the graph. Still looks like this. And then let's say this right here is the point 1, 2. And this is the tangent line. Very sloppy, but let me try one more time here. Okay, close enough, right? So we're looking for the slope of this line. But we don't know any other point on the line, right? We can estimate it, but we don't know it exactly. So here's what I'm thinking. Let's pick another point on the graph. Right, so this is the graph of the parabola, x squared plus x. So we have the point x. So right, somewhere down here is x. This, of course, is 1. So it's a little bit to the right of 1. Right? But for now, let's just call it x. And then the y-coordinate, of course, is given by x squared plus x. Okay? So we can find the slope of the line through these 2 points. Right? So I'll call this ms for secant line. It's a secant line as opposed to the tangent line here. And you might say, well, who cares? I'm looking for the slope of the tangent line, not the slope of the secant line. And you can see they're different lines, so they will have different slopes. So that's true. When we find the slope of the secant line, it won't be the same as the slope of the tangent line. Right? It might be close, but it won't be exactly right. But again, we tried finding the slope of the tangent line. Right? So this is mt, and all we could come up with is this 0 over 0, which doesn't make any sense. That's not a number, right? So let's find the slope of the secant line, right? So yep, I'll call that ms. So we have our 2 points. We have x1, y1, and we have x2, y2. We could have done it the other way, but this is good enough. Let's plug everything in, right? So instead of x2, instead of y2, right? So, this is x2, and then this is y2. So instead of y2, it's going to be x squared plus x. That's the y coordinate on the graph, right? Minus y1. Y1 is down here. Y1 is equal to 2. And then for the denominator, we have x2, which is x, minus x1, which is 1. Okay? So this expression here, right, is the slope of the secant line through these 2 points. Right? This blue line here. Okay, and of course it depends on x, because I haven't nailed down x. I didn't say that x is, 2, or x is 1.6, right? We haven't done that yet, right? I mean, yeah. So this is, this is a little bit more general than we need, but the nice thing is we can apply this to any x, right? Not just a particular value of x, right? Yeah. So with that in mind, what x's should we pick here, right? So again, this is our slope. And just to emphasize that it is a function of x, it does depend on x. It's just the function x squared plus x minus 2 all over x minus 1. And it's a rational function. We've seen these before, right? So, yeah, so maybe let's just make a table. And let's plug in different values of x here. Okay. So obviously we want to know what happens when x is 1. But we already did that. In fact, you can do that. You can plug that in here. You get 1 plus 1 minus 2. So 2 minus 2 is 0 over 1 minus 1, which is also 0. You get 0 over 0 again. So when you plug in 1, it's undefined, right? But we can plug in numbers close to 1, right? Like 1.1, right? Or 1.01, or 1.001. Right? You get the idea. We've done this before, right? Or what's less than 1 is 0.9, 0.99, or 0.999. Okay. Okay, so what do we get? You can, again, I would use a calculator to calculate all these. Just plug them into this function up here. Okay, so here's what my calculator spits out. I'm going to start on the left here. And you plug in 0.9 into, again, this expression here. Let me not cross out the exponent here. Yeah, what you get is 2.9. In fact, let me put those in slightly different color here, right? 2.9. When you plug in 0.99, you get 2.99. When you plug in 0.99, you get 2.99. Sorry, 2.999. There we go. When you plug in, let me go to the right, 1.1, you get 3.1. When you plug in 1.01, you get 3.01. When you plug in 1.001, you get 3.001. So now it should be coming into focus, right? What are these getting close to? Right? Just if you add more zeros, you get 3.0001, 3.000001, and so on. That's getting awfully close to 3, right? It looks like it's getting close to 3. And coming from the other way, coming from the left side, 2.999 is also very close to 3. right? So if we take the limit as x approaches 1 of this expression, just by looking at the table, it appears we get a number 3. So what that tells me is that the slope of the tangent line here appears to be 3. Right? And in fact, you can see that I was right down here. If that's the case, the y-intercept is 0, -1. Right? Remember, a slope of 3, 3 over 1, rise over run, so we go up 1, 2, 3, and we go right 1. So 3 over 1. Right? Makes sense? So it looks right. So I drew the line fairly well. Not great, because it does look a little crooked, but it's close enough. Okay, so there we go. We just computed the slope of the tangent line, but we had to use the idea of a limit here. Right? We had to use this limit. And in fact, we did this using the table, but of course, we didn't have to do that. We could also just do it algebraically. And you can see that doesn't take very long. As long as you know how to factor the numerator, x squared plus x minus 2 is really just x plus 2 times x minus 1. Oops. Too many parentheses. There we go, right? Which means if I cancel the x minus 1s, I guess I should use red for canceling that, yep. When you cancel the factor of x minus 1, you're left with the limit as x approaches 1 of x plus 2. But now there's no problem, right? We're not dividing by 0 anymore. Now I can evaluate the limit by plugging in x equals 1. 1 plus 2 is 3, which of course matches with our previous answer. Right? Yeah. So why can I just plug in 1 here to x? Because x plus 2 is continuous. Right? It's a polynomial. In fact, it's just a binomial. It's a linear function. All linear functions are continuous. Right? All polynomials are continuous. So that's what allows me to calculate the limit by just plugging in x equals 1 here, right? Okay. Anyways, yeah, so in fact, that's our first derivative. So we haven't, I think I mentioned the word derivative, but we haven't defined it yet. So let's do that now. Right? Let's define what is a derivative. So the derivative of a function, in general, f of x, I'm not sure how I want to do this. So let's say the derivative of a function at a specific point. Let's say at x is equal to a, right, is going to be a number. And we can write that number down a couple of ways. We can write it as f prime of a, right? Or we can write it as dy over dx evaluated at x equals a. So that's a little that's a little cumbersome to write it that way, but it means the same thing as f prime of a, right? So this is Newton's notation, and this is Leibniz's notation, and we're going to go back and forth. You should get accustomed to both notations here. We're going to use both. Okay, so what is the derivative? Well, it's a limit. This is why we spent a whole chapter on limits. The whole idea of a derivative involves the notion of a limit, right? So here it is, right? It's the limit as delta x approaches 0. Again, delta x is just some small change in x, right? So it's the limit as delta x approaches 0 of f of a plus delta x minus f of a all divided by delta x. So in order to calculate a derivative, right, we have to calculate a limit. This is the definition. Right? So notice that what we did up here was calculate the derivative at x equals 1, right? At x equals 1, because that's where the tangent line is, at x equals 1, right here. But we could do this for any value of x. In fact, we just picked x equals a. Right. So we're essentially going to do the same example here. But I'll call it example 2 because it's going to look different. Find the derivative of the function f of x. And we'll use the same function. It's still x squared plus x. But instead of doing this at x equals a, oh, actually, let's do it at the same point, at x equals 1. Right? So at x equals 1. Right? Right. In other words, we want to find f prime of 1. Okay, so here a is 1. Right? A is 1 in this case. All right. So let's do it. Let's just use the definition here, right? This is going to be the limit as delta x approaches 0 of f of a, but remember, in our example now, a is 1, so 1 plus delta x minus f of a, but again, a is 1, all over delta x, right? So delta x has nothing to do with a. Delta x is just another quantity, right? And it's a small quantity, right? Because it's approaching 0. It's close to 0, right? So how do we evaluate this limit? Well, again, what we don't do is plug in delta x equals 0, right? If we do that, we get, well, f of 1 plus 0 minus f of 1 divided by 0, which is, again, 0 divided by 0. Okay, so don't do that, right? We can't plug in delta x equals 0 because this whole expression here is not continuous at 0 for delta x equals 0. Instead, we just do a little bit of algebra here, right? Oh, so, yeah. So again, this is nothing new. We've done problems like this before. As delta x approaches 0, so what is f? F is x squared plus x, right? So x squared is now 1 plus delta x squared plus x, which is 1 plus delta x, right? And then minus f of 1. So what is f of 1? It's, well, 1 squared plus 1. Right? So just to make it clear, this expression here is your f of 1 plus delta x, and then this expression here is just f of 1, and we're taking the difference, right, of the difference quotient. Right? Okay. So before we take the limit, let's just expand all this out. So this is going to be 1 squared, which is 1, plus delta x is 2 delta x, plus delta x squared. Okay, so I just FOIL this out, this expression out up here, just multiply it by itself. And then 1 plus delta x, we don't have to do anything with that, just 1 plus delta x. And then minus 1 plus 1 is 2, still over delta x. Okay, so yeah, as it turns out, I didn't need quite as big of a fraction as I thought. Okay, so now what do we do? Well, let's start with just, well, first of all, we still have to write the limit. That comes at the end. Right. And now let's look at the numerator, right? Let's start with the numbers. We have 1, right? Plus 1 is 2, and 2 minus 2 is 0. So the numbers all just add up to 0. Right. What else do we have? Well, we have 2 delta x plus 1 delta x, there's an invisible 1 here, right, is 3 delta x. Right. Plus delta x times delta x, which is just delta x squared, right, all over delta x. So just simplifying the numerator a little bit, and that looks a little bit better. We still need the limit. We haven't done that yet. We don't need the 0, but notice that I have a delta x here and a delta x here in both expressions, right? So I can factor it out. I can factor out one factor of delta x, and what does that multiply? It multiplies the 3, and then in the second term here, it multiplies another delta x. So using brackets here. And of course, there's a delta x in the denominator. So I hope you know where this is going now, right? Delta x divided by delta x is 1. So they cancel. So what are we left with? Just 3 plus delta x. So what happens as delta x gets close to 0? Well, this gets close to 3 plus 0. It gets close to 3. Again, no surprise, because we did that already. We got the slope of the tangent line equal to 3. Right? So it's the same 3 here as it is down here. Okay? So yeah, the derivative is just the slope of the tangent line at a particular point. So again, this concept of the derivative here takes a little getting used to, right? And we just did one example. We'll do a few more because this is an important concept here. But what are we doing when we're finding the derivative, right? So the derivative of a function, f of x, at a specific point. Again, we've been using x equals 1 here, but it could be, it could be at any point. We'll just say x equals a, right? So this is going to be the slope of the tangent line to the graph of the function. So to the graph of y equals f of x, specifically at x equals a. Right? Well, or the point on the graph, right, is a f of a. I don't want to use too many parentheses here. Right? So at the point a, comma, f of a is the y-coordinates, right? In our example up here, the y-coordinate was what? The y-coordinate was 2. So that's f of 1, or in this case, in general, f of a. Okay, so that's what the derivative means. You take the derivative if you want to find the slope of a tangent line. Okay. But it also means something else, something we referred to earlier. So the derivative of, I'll call it another function, say s of t, all right, at t is equal to a, is the instantaneous rate of change. Of the function s of t, again, at t equals a. Right? So, for example, if s of t is the position at time t, then the derivative, which, remember, there's two ways of writing this. Here it is, right? I don't know what happened, f prime of a or dy by dx. So in this case, this is going to be s prime of t, I'll call it s prime of a, or the derivative of s, ds, divided by dt, evaluated at t equals a. Right. So if this is the position, the rate of change of position is the velocity at time t equals a. Okay? Yeah, So the derivative of position is velocity. I'll just write that down. Right? The derivative of position is velocity. Okay. Oh, so I'm running out of space. I think let me, yeah, let me first of all go back and, right, so that's the derivative of s. So because it's velocity, we can also just call it v, right? So v of a for velocity is just s prime at a. When you're talking about the derivative of f, right, we can write it as dy over dx or f prime of a. Oh, I forgot to plug in the x equals a here, right? So I think I mentioned that before up here. Right. So let's suppose I think I can squeeze this in here. This will be example 3, I suppose. Right. Suppose s of t is just a function t squared plus t. Right. And we want to find the velocity at time t equals 1. So how do we find the velocity at time t equals 1? Well, the velocity at time t equals 1 is the derivative of the position at time t equals 1. Right? And we already took the derivative of this function, right, at time t, at x equals 1. So that has to be 3. Okay. And again, we didn't give units here, so 3 meters per second, let's say, or 3 miles per hour. It's, right? But yeah, don't get confused with s of 1. Right? S of 1 was 2. Right? S of 1 was just 1 squared plus 1, which is 2. Right? So that's the position at time t equals 1. So we're at a position of, say, 2 meters. But how fast we're going, that's 3 meters per second. Right? So S tells you where you are, and S prime, or V, tells you how fast you're going. Right? Okay, so that's the idea of the derivative. Let's do a couple more examples, I guess. Okay, actually, before we do another example, I just want to go on to the concept that the derivative of a function, because before it was a number, but it's actually just another function, right? And we can call it f prime of x. So instead of plugging in x equals a, we're just going to leave the a and leave it as x. Okay. So one way to write it is f prime of x or dy by dx. So the dy over dx, again, be careful you don't cancel the d's, right? Don't do that. It's not y over x. The d is just what's called an infinitesimal. It's a tiny, tiny change in y, right? And it's essentially like the delta y over delta x, right? Except here, delta x is approaching 0. And of course, what happens is if the denominator approaches 0, the numerator also approaches 0. Right? But again, it doesn't equal 0, right? It's not 0 over 0, which we already know is nonsense. So don't make that mistake. Instead, this dy over dx is like, think of like the next biggest number after 0. Right? I mean, technically there is no next biggest number after 0, but the dy sort of behaves like a number that's very close to 0, but not exactly 0. Okay. So what is this delta y? The delta y is just the change in the y's, right? So it's essentially y2 minus y1. And over here on the right, the y2 is f of x plus delta x, and the y1 is f of x. So this is y2 minus y1. And of course, the delta x is x2 minus x1. But x2 is x plus delta x, and then x1 is x, so x minus x is 0. That's where you get the delta x from, right? So I hope you understand this picture and how you get this this idea of the derivative here, right? In particular, here I want to get rid of this clutter here. Okay, so if you look at this expression here, f of x plus delta x minus f of x divided by delta x, right? This is the difference quotient. This is what you did in pre-calculus many times, right? So this is not the derivative, right? If you like, this is the average rate of change of the function, right? Or it's the slope of the secant line passing through 2 points. It's not the derivative. How you get to the derivative is you take the limit, right? So the derivative is the limit of the difference quotients. Okay. All right, so now let's do an actual example. So I think we're up to 4 now, right? So find, let's say f prime of x. Okay, so that's not a 1, that's a prime, meaning the derivative. For, let's say f of x is equal to, I'm going to make this a little bit tricky here, x cubed minus 4x. Okay, so we're looking for the derivative of the function x cubed minus 4x. So how do we do that? Well, let's just write down the definition. F prime of x, derivative of the function is going to be the limit as delta x approaches 0. If you're looking at Khan Academy, you'll notice that Salcon uses h instead of delta x. That's fine. If you want to use h, that's fine. I'm going to stick with our book, which uses delta x. Okay, so limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Right. And this is something that comes up a lot. You probably should know this. Just the definition of the derivative. But of course, you can also just look it up. But you know, if you have to look it up every time, you might be wasting some time there. So this is good to know, the definition of the derivative. All right, so how do we calculate this? Well, right, so the hard part, I think, is what is this f of x plus delta x? So I'm going to do that, yeah, I'm going to do that way over here. In fact, I'm not going to go left to right here. I'm going to go vertically. So my next step will be down here. But, yeah, so let's see, I'm running out of colors here. I'll use orange. So what is this f of x plus delta x? Oops, I erased too much here. Okay, so f of x plus delta x. So everywhere we see an x, we just have to replace it with this expression here, x plus delta x. So instead of x plus delta x, instead of x cubed, it's x plus delta x cubed minus 4 times x, but instead of x, it's now x plus delta x. Okay, so I'm just substituting for x this expression in here, right? This x plus delta x instead of x. Okay, so now we're making some progress here. Yep, so the f of x plus delta x is x plus delta x to the 3rd power minus 4 times x plus delta x, right? And then we just subtract f of x. So f of x is just this, right? It's x cubed minus 4x. Again, don't forget the parentheses because you want to subtract the whole thing. Okay. Now we have a lot of work to do here. What is x plus delta x cubed? So to do that, properly, you would have to do x plus delta x times x plus delta x times x plus delta x, and then minus 4 times x plus delta x, right? So doing all this out, just step by step, takes a while. So I'm going to do this all at once. I'm essentially going to use the binomial theorem. If you know the binomial theorem, you can take the shortcut. If not, well, then you got to do it step by step. So FOIL this out, and once you get that, multiply by another x plus delta x. But that's going to be kind of tedious. So I'm going to do this all at once. I'm going to do x to the third power plus 3 times x squared times delta x plus 3 times x times delta x squared plus delta x cubed. Okay. Right. So if you're doing this the long way, this might take you a few minutes, but that's all that is. All right. Now, the minus 4 times x plus delta x is just minus 4 times x minus 4 times delta x. And now let's distribute the negative sign here. So we're going to get negative x cubed, and then minus a negative 4x is plus 4x, all divided by delta x. Okay, so I'll give you a minute to just process all that. That's a lot of algebra we did here. Most of it was involved in figuring this out. You get this lengthy expression here. Again, doing it the long way, this might take you a couple steps to do that. I did it all at once because I know the binomial theorem, Pascal's triangle. Right, where do the 3's come from? 1, 3, 3, 1. So I'm using this row of Pascal's triangle where you get 1, 3, 3, and then another 1. Okay, so that's the shortcut. But if you don't know Pascal's triangle or the binomial theorem, just do it the long way. All right, so now getting back to the algebra, you can look at this expression in the numerator here, and you notice I have a negative x cubed, but I also have a positive x cubed. So that adds up to 0. I also have a negative 4x and a positive 4x. That adds up to 0. But I think that's it, right? So nothing else cancels other than those. So after we get rid of everything in red here, what are we left with? 3x squared, times delta x plus 3x times delta x squared plus a delta x to the third, and then minus a 4 times delta x. So that's a 4. Okay. All over delta x. Sorry, that's my delta x there. All right. Now there's a couple things you could do. You could split this up into 4 separate terms. But the way I like to do it is, here's a delta x, here's a delta x, here's a delta x, here's a delta x. All 4 terms in the numerator have a factor of delta x. So that's our greatest common factor. It means we can factor it out. What was that? Oh, this was a parentheses here, sorry. Okay. Yep, so factor out the common factor of delta x, and what does it multiply? 3x squared plus 3x. Oh, to get delta x squared, we need another delta x. And then to get delta x cubed, we're going to need a delta x squared, and then minus 4. All divided by delta x. And, I haven't used parentheses yet, but it's not necessary, but you can. Right, so now we can cancel the delta x's. So we can do that because delta x is not 0. It's just something close to 0, but it's not equal to 0. At least not yet. So now to take the limit, what do we have? We have 3x squared delta, 3x squared plus 3x delta x plus delta x squared minus 4. Okay, so again, all of this algebra here was to get rid of that pesky denominator, because up until that point, we would be dividing by 0, right? as delta x approaches 0. But now the denominator is 1, which is not 0. Right? So now there's no problem here. All we have to do to take the limit is notice that this is a continuous function at delta x equals 0. So now we can just plug in delta x equals 0. We get 3x squared plus 3x times 0 plus 0 squared minus 4. Okay, so anything times 0 is 0, right? So 3x times 0 is 0, and 0 squared is 0. So all that's not 0 is the 3x squared minus the 4. And that's it. So that's our answer. So what is 3x squared minus 4? It is the derivative of this function here. So let's write this down. All right, so f of x is equal to x cubed minus 4x. Then we get the derivative of f. And after doing all this, the derivative is just 3x squared minus 4. And we're done. Right? Again, not easy, not a simple process. It takes a while. It takes a lot of getting used to here. And it's a lot of algebra. Right? Now, I know a couple of you are thinking, wait a minute, I knew this. I didn't have to go through all this. This is easy. Just bring the 3 in front, right? Decrease the exponent. So, yeah, of course, you're using the rules for derivatives. And if you know the rules, you don't have to go through all this, of course. But I'm assuming that most of you don't know the rules for derivatives yet. We haven't talked about those yet. Those are coming up after the test, after the first test. So the rules will be on the second test. Right? So the rules are properties of derivatives. So I should have been clear here, right? When I say find the derivative, what I should have said was using the definition, not the rules. So that would force you to do it this way, right? So yeah, you can't just write down 3x squared minus 4, even though it is that easy. Okay. So yeah, if you don't know what the rules are, right, you're finding the derivative using the definition here, right, which means using this limit, finding this limit. Okay. And yes, it's a real pain. Right? It's a lot of algebra. It's not pleasant, but it's something you should get used to. On the other hand, right, some of you already know this. Those of you that don't will realize that, yeah, there's a very quick and easy way to get this. And some of you already know how to do it the easy way. Right? But we're not there yet. Right? Right? We want to know the meaning behind this definition up here. Right, that it's the slope of the tangent line or the instantaneous rate of change. Okay, so yeah, once we learn the rules, we can think of those rules as a shortcut to go from here to the derivative very quickly, very easily. Right, but it's a lot of rules, and you have to memorize them. You have to know them. Right, so until we know those rules yet. Until we get those rules, we have to do it by using this definition up here. Okay? So for this section, for section 2.1, we're going to be using the definition, right? This is in section 2.1. After this section, the rest of chapter 2, then we can take the derivative using the shortcut. But in this section, and that means on the first test, if I ask for the derivative, and you just write down the answer, you're not going to get any credit for that. You have to go through this horrible process. It's not horrible. It's just tedious. It's just a lot of algebra. But, you know, presumably you've done most of the algebra before. The only thing new about this is at the very end when you take the limit. So in your pre-calculus days, we ended with this expression here. We left it at that. And this expression would be the slope of the secant line, or the average rate of change of the function. But now we can find the slope of the tangent line, or the instantaneous rate of change of the function, by taking the limit and getting the derivative. So that's the new part, is only at the very end. And that's the easy part, right? Taking the limit just means plugging in 0 at the end. But you can't plug in 0 at any stage before that, right? You cannot plug in 0 at the beginning because, well, it's in the denominator. And you know you cannot divide by 0. So, right, so you have to go through this algebra, cancel the delta x's eventually. That comes at the very end. And then you can plug in 0 to take the limits. Okay, so I hope that helps. Yeah, and in fact, for our next example, yeah, example, I guess 5, we're going to find the slope, or actually, let's do even more than that. Let's find the equation of the tangent line to the graph of the function f of x equals x cubed minus 4x at the point, let's say x is equal to 2. No. All right, let's do x equals 1. X equals 1. Okay, fair enough. X equals 1. So, of course, first thing you can find is y. Y is just f of 1. So that's going to be 1 cubed minus 4 times 1. So 1 minus 4 is negative 3. So I didn't give you that information. I could have, but I said at the point 1, negative 3. Okay. So what do we need for the equation of a line, of any line, right? So the equation of the line passing through the points, let's say x0, y0, with slope m, so m refers to the slope. Well, there's a lot of ways you can write this equation, but the way you should be familiar with it, I hope, is the point slope form. Y minus y0 is equal to m times x minus x0. So this is sometimes referred to as the point slope form. You can guess why, right? You have a point, you have the slope. That's all you need. You need one point on the line, and you need the slope of the line. That's enough to find the equation. Okay. So yeah, we're just going to plug in the specific values here. We know that x0 is 1, and y0, well, we had to find that, but that's just the negative 3. So we get y minus negative 3 is equal to, well, we haven't found m yet. And x0 was 1, right? X0 was 1. So yeah, the hard part, of course, is finding m. So what's the slope of the tangent line? Okay, so if you're doing this, you're not going to get it, right? Because this requires 2 points, and we only have the 1 point. This is the only point on the line that we know. Okay, so this is if you know 2 points, and we don't have that information. Right, so we're not going to use that. Instead, we're going to use the fact that the slope of the tangent line is the derivative of the function at our specific value of x, right, at x equals a. In our case, we're doing this at x equals 1, so a is 1. Okay, so what is f prime of 1? So how do we find f prime of 1? Well, we need the derivative, right? You don't plug in 1, right? You don't plug in 1. We did that already. We found that f of 1 is equal to negative 3, but that's the y-coordinate. That's not the slope at 1. To find the slope, we need the derivative. So how do you find the derivative of this function here? Well, we already did it. We're not going to do it again. We did it up here, right? So here's the function, the same function, x cubed minus 4x. And we did all this, and we got our derivative, which is right here, 3x squared minus 4. So yeah, because it's way up here, let me copy it down. F prime of x equals x cubed minus, sorry, that was the original function, x cubed minus 4x. The derivative was 3x squared minus 4. Okay. So now just plug in 1. Right, so 3 times, I didn't mean to do red. Oh boy. All right, so I'll continue in blue here. This is 3 times 1 squared minus 4. 3 minus 4 is negative 1. Okay, so that's my m. So that's my m. So I can erase this m here and just put in negative 1. Right. And then that's the equation of the tangent line. Now, this is probably not the best way to write it. When I'm looking for the equation of a line, I am looking for the usual form, y equals mx plus b. Okay, so how do we go from this to this? Again, that's just a little bit of algebra here. So y minus negative 3 equals negative 1 times x minus 1. So negative 3 is positive 3, right? And then we can distribute the negative 1 here. This is negative 1 times x, or just negative x, plus negative 1 times negative 1, which is positive 1. Okay, right? So we're just solving for y. So we can just subtract 3 from both sides. So y is going to equal negative x minus 2. Right, so that's the equation of the tangent line. Right. Passing through the point 1, negative 3, and it's the tangent line to the graph of x cubed minus 4x. Right. Okay, so again, when I ask for the equation of a line, I like y equals mx plus b, although the Larson book apparently doesn't like that version. Larson likes the following version. It likes ax plus by plus c equals 0, which is sometimes called the general form of a line, right? This is the slope-intercept form. Slope y-intercept form. This is the general form. So how would you write it in general form? Just add the x to both sides. Right, and some people even write it this way, but they also want you to add the 2 to both sides. So the book would write it as x plus y plus 2 equals 0. And in fact, I'm not going to be picky about that. You can write it either way you want here, right? Either in slope-intercept form or general form. Just don't leave it like this, because this is kind of a mess, right? This you have to clean up a little bit, do a little bit of algebra that we did here. Okay. Okay, so in other words, simplify, right? Simplify till you get to either this answer, which looks pretty nice, or this answer, which is the way the book prefers it, but you know, I'm not picky. My preference would be slope-intercept form, but I'm happy with general form too. I'm happy with this. And in fact, in some cases, you don't have a choice. In some cases, you have to write it this way. When you're talking about vertical lines, remember, vertical lines don't have a slope. Right? The slope is undefined for vertical lines. So you can't write it in slope-intercept form. You have to write vertical lines this way in general form. And those are usually easy here. Vertical, what am I? Oh, undefined. Don't worry about that. Right? Vertical lines don't have a slope. Right? It's not 0. Right? If the slope is 0, hopefully you remember that that's a horizontal line, not a vertical line. The vertical lines have, right, undefined slope. That's what I was trying to write down here, but I got a little sloppy here, right? Okay, in any event, I'm not going to worry about that. Yeah, so vertical lines usually have equations like, you know, x equals 5. much simpler, right? But there's no m, and in fact there's no y either. Y could be anything. Okay. So that's, again, just an application of this example. Example 4, we found the derivative, and then we use the derivative to find the slope of the tangent line. Right? Or, we'll do one more here. And I know I'm using colors all over the place here, but typically I like to write the problem in blue and then answer in either green or yellow. All right, so let's suppose we're given a function s of t is equal to t cubed minus 4t. And this will be the position function of some object. It doesn't matter. It could be a car. It could be a spaceship traveling in space, right? It doesn't matter. It's the position of some object, right? We want to find the velocity at time, let's say t equals 6. And I'm not using units here, right? So this could be 6 seconds, and this could be in meters. But so our answer will just be a number for now. Later on, we'll give you units, feet in seconds or meters in seconds, usually. Right, so how do we find the velocity? Right, at that moment in time, at time t equals 6, right? So notice, it's not average velocity, right? It's instantaneous velocity. I didn't write the word instantaneous. But we know it has to be instantaneous because we're given an instant in time. T equals 6 is not a time interval, right? If I said, time t equals 2 to t equals 6, from 2 to 6, that's 4 seconds, right? That's a 4-second interval. Right. So if I gave you that, you would be finding the average velocity. Right? But that's not what we're doing here. We want the instantaneous velocity. We're only given one moment in time, t equals 6, one instant. So so for that, we're looking for the instantaneous velocity, not the average velocity. So to find the instantaneous velocity, the only way we know how to do that is if we can find the derivative of the position function, right? S prime of t, or ds divided by dt, same thing. Right. And luckily, we found that derivative already. Just to remind you, it's 3t squared minus 4. So just change the x to a t now. Right. So this is the derivative at any time. And maybe I didn't emphasize that enough up here. Let me go back to this example up here. Find the equation of the tangent line at x equals 1. So I just, again, that was the question at x equals 1. We could have given you x equals 2 or 3 or -7, right? See, that's the advantage of finding the derivative as a function of x, right? As a function of x, you can plug in any x you want after you find the derivative. Once you find this derivative here, it's a function of x. You can plug in x equals 1, 2, 7.4. It doesn't matter. Any number that's at least in the domain, right? So, so here's the derivative, but specifically we want the velocity at time t equals 6. Right? So now I can just plug in t equals 6. Sorry, that's supposed to be a prime. Okay. So, here's the derivative. Change t to 6. So 3 times 6 squared minus 4. So be careful. You're not doing 3 times 6 yet. You got to do 6 squared first. 6 squared is 36. Now 3 times 36 is 108. And then minus 4, 108 minus 4 is 104. It's a crummy looking 0. So 104. Again, I didn't give you units, but it could be meters per second, feet per second, miles per hour, kilometers per hour, right? But for now, it's just 104 distance over time. Right? So that's how fast it's going. That might seem like it's awfully fast, but that's the velocity. Right. do not get confused with position. If I plug in 6 into the original function, I get 6 cubed minus 4 times 6. So let's see, that's going to be 216 minus 24. And 216 minus 24, I want to say is 188. Don't quote me on that. I'm doing this in my head. I don't have a calculator. 216 minus 24. Okay, so I'm wrong. It's 192. It's 192. All right, so I was close, but not quite. Okay, so that's not velocity, right? This is position. Right? This tells you where you are. You're at the position of 192 meters, feet, miles, kilometers, whatever units of distance we're using. Right? So this is a distance. Right? This is a distance. This is where you are. This is telling you how fast you're going. Right? This is your speed. So again, velocity and speed, not quite the same thing. Velocity is telling you which direction you're going in. You're going 104, feet per second, meters per second, in the positive direction. Right? And we never said what the positive direction is. It could be to the right, right? It could be going up. It could even be going down, right? Down could be positive, right? It could be left, could be positive. But, we didn't say what direction that is, right? So in this case, your velocity and your speed happen to be the same thing. But if you get a negative number here, if it's negative 104, that's not your speed. That's your velocity, right? Okay? So I hope that helps. Okay, moving on. Next example. Find dy over dx, that's the derivative of y, for y equals 1 over x squared. Using the definition, right? So for those of you, and again, some of you who've had calculus before, may remember that there's a very quick way of doing this, of course. But in this case, we can't do it that way because the directions specifically say to use the definition of the derivative. So to do that, we have to take the limit as delta x. Of course, if you want to say h goes to 0, you can use h instead of delta x. That's fine with me. But I'll stick with delta x, right? So this is, right, I guess we didn't call this f of x, but we can do that here. So f of x is just 1 over x squared, right? Which is also x to the negative 2. And in that form, now some of you probably know the derivative already, but most of you probably don't, right? Most of you have not had the rules for derivatives yet, which is fine because we're not going to use those now. So, actually, let me just copy down the definition one more time here. So this is f of x plus delta x minus f of x over delta x. Again, that's something you should know. Now let's apply it to this particular function, or f of x, right? So again, the limit comes at the very end. We have to keep writing limit. If you don't, it's wrong, right? So what is f of x plus delta x? Well, I'll tell you what it's not, right? It's not 1 over x squared plus delta x. It says, don't make that mistake, right? That's something you might have done. I know we've all made that mistake at some point, I think. So let me be very clear here that if you write f of x plus delta x is not the same as f of x plus delta x. In other words, right, it's not just 1 over x squared and then you tack on a delta x. If you make that mistake, I'll tell you what you get. You're going to get 1 as your answer. Right? You're always going to get 1. Right? And that could be the derivative, but that's pretty rare. If you're always getting 1 as your answer, then you're always making this mistake. So don't make that mistake. Right? So what do we do instead, right? Instead, we replace x with delta x. So instead of 1 over x squared, right, we change the x to what's in the parentheses, x plus delta x. So that's the thing we square. Okay. So I'm just going to rewrite that up here. 1 over x plus delta x, quantity squared, minus f of x. Well, f of x is just 1 over x squared. I didn't mean to put that arrow there, but that's what f of x is, right? 1 over x squared. Right. And then the denominator, of course, is still just delta x. Okay, so it's a good place to start, right? And if you're thinking just replace delta x with 0, well, that's not going to work because we'll be dividing by 0. So again, most of the process here involves a lot of algebra. It's just simplifying all this mess up here. Okay. And there's a number of ways, a couple of ways we could simplify all this. I'll show you my favorite way, and then you can do it your own way. My way involves the denominator here in the numerator, right? In the numerator here, if we want to get rid of these denominators, we can multiply by the LCD, the least common denominator. So the least common denominator has to involve the x squared, so it has to contain x squared. And it has to contain the other denominator, which is x plus delta x squared. Has to be both, right? But if you multiply the numerator by this, you have to multiply the denominator by the exact same thing. Right. Why? Because this is just 1 here. I mean, essentially, these cancel, and you're just multiplying by 1. But if you cancel these, well, then you're back to square 1 again, and that doesn't help. Okay. So instead, think about what we're going to do. We're going to take this expression here and just distribute it inside the little brackets here. We're going to multiply this one times x squared times x plus delta x squared, and then this one over here as well. Sorry, I crossed out the delta x, but all right. So let's do that on the next step here. Oops. Okay. So right, limit delta x approaches 0. So instead of 1, it's 1 times x squared times x plus delta x squared, all over the same denominator, x plus delta x squared, minus, because this is a minus here, right? Instead of 1, it's x squared times x plus delta x squared, all over x squared. Right? Now, there's also this whole big denominator here, which involves delta x times x squared times x plus delta x squared. Yeah, what a mess, right? This does not look nice. But look at the numerator, the fractions in the numerator carefully here. If you look at this carefully, you'll notice that these are the same factors, which means they cancel. For the fraction on the right, this x squared divided by x squared is also 1. So they cancel. Okay, so that is the simplifying that we need to do to create just a simple fraction. No more fractions within fractions within fractions and so on. Right? So the numerator here is just x squared minus, and then what we have in parentheses here, x plus delta x squared. And then this denominator, I'll just copy this down here, if it's okay with you. This is still going to be delta x times x squared times x plus delta x squared. Okay, moving on. The next step, I don't think we can take the limit just yet because we'd still be dividing by 0 at this point. But notice what we can do in the numerator here. So I'm just going to copy the denominator down, maybe one more time. But the numerator we can simplify. The numerator is just x squared minus, and then in parentheses, right, FOIL this out up here. You're going to get x squared plus 2x delta x plus delta x squared. And then don't forget to distribute the negative sign. That's why we need, oops, not to the delta x, but to the delta x squared, right? So distribute the negative sign. That's why we needed parentheses there. This is a 0. All right, x squared minus 2x delta x minus delta x quantity squared. And then the denominator, same thing for now. I'm just going to copy it down. I did say one more time, right? Maybe one more time after this. Okay, well, x squared minus x squared, of course, is 0. So that just adds up to 0. You can say they cancel. So notice what's left in the numerator here. We have an x squared here. We have an x squared here. We can factor that out. Wait, did I say x squared? I'm sorry. I meant delta x. We have a delta x here and a delta x here. Boy, I'm getting sloppy. Sorry about that. Yes, delta x is the common factor. We can factor that out because that multiplies a negative 2x and a minus delta x. Now I think you can see where this is going, right? This was a pain, but now we're almost done. Because delta x divided by delta x, these are factors now, you're just multiplying. These are allowed to cancel. You can cancel those. Okay, and finally, now I think we can take the limit here. We have negative 2x minus a delta x in the numerator, and then in the denominator we have x squared times x plus delta x squared. Okay, now there's really no issue. Now you can just replace delta x with 0. And you might think, wait a minute, isn't there a delta x in the denominator? Are we going to be dividing by 0? Nope. Nope, these are 0. Let's see what happens, right? Well, we still have to take the limit, but the numerator will just be negative 2x minus 0 divided by x squared times x plus 0 squared. Okay, oh, actually, we didn't need to take the limit. We're taking the limit now, right? By replacing delta x with 0, this is what we get, right? So this should be the answer. And notice the numerator is just a negative 2x. The denominator is x squared times x plus 0 squared, but x plus 0 is just x. And x squared times x squared is x to the 4th. But remember the rules of exponents. 4 minus 1 is 3. So this is just negative 2 over x cubed. And there's our derivative. Okay. Yeah, so that was the derivative. And again, as a function of x, right? So let me just remind you, the original function, f of x, which I called y, right, same thing, was 1 over x squared. And we found the derivative of that function, f prime of x, or dy over dx, is equal to negative 2 over x cubed. And we're done. Right? So what does this represent? It represents the instantaneous rate of change. Forgive the sloppiness here. Rate of change. Or the slope of this tangent line. So we talked about both interpretations of the derivative. One is geometric, having to do with the graph and the slope of the tangent line. The other is a physical problem where you have motion, right? Something moving. You have position. The instantaneous rate of change of position would be velocity. But more generally, just instantaneous rate of change. Like this doesn't have to be position. This could represent your cost function. X might represent the number of units, and and then F might represent how much it costs to produce that many units. So then the derivative of that will represent, well, what's sometimes called the marginal cost, or the cost per unit. Right? So the rate of change of the cost, as you add units, how much more does it cost you? That kind of thing. But anyways, so we'll talk about a little bit more about instantaneous rate of change again a little bit later. But yeah, so now you plug in your x equals 7, right, and you get the slope of the tangent line at x equals 7. Or if this is for 7 seconds, you plug in 7 and you get the instantaneous velocity at that time, 7 seconds, right? Okay. Yeah, again, this was a long example. This was a lot of work, a lot of algebra here. Again, it's algebra you should have done before, but it's easy to forget, and it's easy to make silly little mistakes here, so just do it carefully. And yeah. Now, to be fair, they're not all going to be this bad. This was a particularly difficult one because it involves these compound fractions, fractions within fractions, getting a common denominator, right? They're not all going to be that bad. They're not all going to be that bad. And so maybe we'll do a simpler one just to show you that sometimes they're pretty easy. Yeah. So let's just do a very easy one now. And I lost count of how many examples this was. This was 7, so I guess we're at example 8 now. Okay, let's switch to g of x. G of x is the function 5x plus 9. Right. Find the derivative, again, using the definition. So no cheating, right? Obviously, some of you recognize the answer right away, right? And it should be obvious here. But if it's not, don't worry about it. We'll use the definition, and looking back, we'll see, oh yeah, that had to be the case, right? Okay. All right. So again, what's the definition of the derivative? Well, it involves this limit here. And if you're wondering, why do we have to go through this if the answer is obvious, if we really know it? Well, yeah, I mean, look, we're not going to be doing this that much longer, right? Just for this one section and just for this test, we got to get used to the definition, right? We want to know where it comes from, right? The definition is sort of this intuitive idea of, you know, the slope of the tangent line or the instantaneous rate of change. Right? So without the limit here, of course, it's the average rate of change, or the slope of the secant line. With the limit, when you take the derivative, you get the slope of the tangent line, or the instantaneous rate of change. Okay, this will be a quick one. Right? What is g of x plus delta x? So just change, right, the x here to x plus delta x. And you get 5 times x plus delta x plus 9. Right? And then minus g of x is still 5x plus 9. Okay. Again, you should really be able to take it from here. I'm hoping you work this out before you watch me do it. Distribute the 5. Okay. Okay, so 5x plus 5 times delta x, it's a 5, not an s, plus 9, and then minus, distribute the negative here. This is why you need parentheses, right? It's minus 5x minus 9, right? If you make the mistake of doing plus 9, well, you're out of luck, right? You're going to get the wrong answer, or it's not going to work out. It's just not going to work out. It is a minus 9, right? And then all divided by delta x. So now we can cancel a lot of things, right? 5x minus 5x is 0, and 9 minus 9 is 0. So now we're just left with, oops, I didn't want green. Yellow here. Oh. So this will equal the limit as delta x approaches 0 of 5 times delta x all over delta x. And if you're thinking, well, if I plug in 0, I still get 0 divided by 0. And that's true. But delta, oops, a little less sloppy here. Delta x divided by delta x is 1. Right? It's like 2 divided by 2, right, is 1. Anything divided by itself is 1. So this is just 5 times 1. Right? And what's the limit of 5 as delta x approaches 0? Well, there is no delta x, right? It doesn't depend on delta x. It doesn't matter what delta x is, right? Delta x could be approaching 5,000 or negative 28. 5 is 5. 5 is a constant. So the limit of 5 is 5. Okay. And then that's the derivative. Okay. So g prime of x, here it is again. G of x, the original function was 5x plus 9. And then the derivative of that function is just the number 5. Okay. So why did I say that was obvious, right? Because I know some of you probably didn't see that, right? And that's okay. It's not obvious, well, you know, it's not obvious to everyone. It certainly wasn't obvious to me, you know, many years ago. But here's why I'm saying, in retrospect, now it makes sense. Right? Let's draw the graph of this function here, g of x. It's just a straight line, right? This is y equals mx plus b. Right? The slope is 5 and the y-intercept is 9. I'm going to put 9 way down here. And, you know, 5 is pretty steep, so it's a pretty steep line here. Oops. And it's a very sloppy line. So maybe let me try that one more time. It's a little better, right? So, so remember, the derivative is the slope of the tangent line. Well, what's the tangent line to this line? Well, then you should ask at what point, but it doesn't matter. If you pick any point on the line and you draw the tangent line is the same line. And that line has slope 5. So it doesn't matter where you are on this graph, the slope of the graph is the same everywhere. It's a constant, right? The slope is 5. Okay. When you go back to the previous examples, and I think I erased all, oh no, I didn't erase them, right? Yeah, in general, your derivative will depend on x, right? Because these are curves. And when you look at the graph of a curve, right, the slope will change. If you look down here, the slope is pretty small, right? It's not very steep at all. But if you look over here at a different value of x, it's going to be much steeper. Okay? So yes, the slope of a graph can change. Right? In particular, what's changing are the tangent lines. The tangent lines have different slopes at different points. Unless you're talking about a line, in which case the slope of the tangent line is the same everywhere along that line. Make sense? Right? So yeah, when the derivative is just a constant, then you know that the original function was a straight line. Because that's the only type of graph, right, where the slope does not change, is a line. Okay? Good. Okay, one last example, but an important one. Okay? Because I think when I wrote down the definition of the derivative, I left something very important out here, right? So here's the function. It's the absolute value of x minus 2. And we want to find the derivative of that function at x equals 2. Okay, so we can write down the definition here. The derivative is going to be the limit as delta x approaches 0 of, well, you know what, actually, I'm not sure what to do. If we want to plug in x equals 2, we could do that now. Well, okay, before we do that, let's just write it down in general, right? So this is going to be x plus delta x minus 2 in absolute value minus f of x, which is just the absolute value of x minus 2, all divided by delta x, right? So this is the derivative for any x But in this problem, we only care about x equals 2, right? So we don't have to figure out the derivative for any x here. We can just figure it out for x equals 2. So now, just replace all the x's with 2's. So this is 2 plus delta x. Now, not this x, right? That x is a delta x. It's not 2. Leave that as delta x. Okay, yeah, don't change delta x to, it's not delta 2, right? It's not 2. It's still delta x, right? So this is going to help us out a lot because notice that 2 minus 2 is 0. So we just get the absolute value of delta x, and then minus the absolute value of 0 is 0, right? So minus 0 over delta x. Okay, so what is this quantity here? What is this? You might think the delta x's cancel and you just get 1. Well, you have to be careful, right? Remember what absolute value is. So absolute value of a could be anything here, right? It's a piecewise function. Remember those? It's going to be a, right, if a is positive or 0, and it's negative a if a is negative or less than 0. Okay, so we really need to split this up into two separate pieces here. And, right, so we're taking the limit as delta x approaches 0 of the following, right? So it's going to be delta x divided by delta x if delta x is greater than or equal to 0. And if delta x is going to be less than or equal to 0, then it's going to be negative delta x over delta x. Okay. So delta x divided by delta x is 1 if delta x is greater than 0, but not equal to 0, right? And it's going to be negative 1 if delta x is less than 0. So remember, we're taking the limit now as delta x approaches 0. So delta x cannot equal 0. So what is the limit of this function here? Right? If it's not apparent, let's graph it. So here's delta x, and here's the function. I don't know what to call this. G of x, maybe? I didn't call it f. Yeah, let's call it g of x. So 1 is just a straight line, right? So here's 1, 2, and so on. Negative 1, negative 2, 1, 2, 3, 4, 5. So, yep, when delta x is positive, this is just going to be 1, which is this horizontal line here. Right? Except, of course, at 0, it's undefined there, right? So there's a hole. For delta x negative, so here's negative, it's going to be negative 1, right? But again, when you get to 0, there's nothing there. Right. It's another hole. Okay? So, yeah. When delta x approaches 0, from the right side, we're getting closer to 1. From the left side, we're getting closer to negative 1. Right? You can't have two different values. It can't be 1 and negative 1. It could be 1 or negative 1, but it can't be both. In this case, it's neither, right? Which means this limit does not exist. I mean, we could, of course, take the limit as delta x approaches 0 from the right of this function, and that would give us 1. We could take the limit as delta x approaches 0 from the left, and that would give us negative 1. But then to get the limits as delta x approaches 0, which means from both sides, I know my zeros are sloppy here. Let's try that again. Right? These would have to be the same number. But positive 1 and negative 1 are not the same, so that tells us the limit fails to exist. There is no limit here. All right, now what does that mean for the original question? The original question is, okay, here's a function, what's its derivative? Well, remember, the derivative is defined in terms of a limit, but not everything has a limit. Sometimes the limit does not exist. And in that case, that means the derivative does not exist. Right? So for the derivative to exist, it has to be a number. Here we don't get a number. We don't get 1, we don't get negative 1, we don't get 0, we don't get anything in between. It just does not exist. Okay? So yeah, if you go back to the original definition, it involves a limit, right? So here's what I should have said, right? That the derivative of f prime of x, is the limit as delta x goes to 0 of f of x plus delta x, right, minus f of x, all over delta x, right? And this is the derivative of f. Right, at x, provided that the limit exists. Right. And if the limit exists, right, in which case we say the following. We say the function f of x is differentiable. It's supposed to be an e. Let's try that again. Right, at x. Okay. It's differentiable at x if the limit exists and you get a number, then that's the derivative, right? Right. So if the limit does not exist, then the function f is not differentiable at x. Okay. So yes, not every function is differentiable, and this one up here, the absolute value function, is not. And just to show you what that means, right, let's look at the graph of, again, the original function, not the derivative. Right, so just to be clear, this function here, that what we graphed here is the derivative. We want to graph the original function. The original function was just the absolute value of x minus 2. Okay, and that's going to look like this. Okay, so it's just the absolute value function shifted right 2 units. So it's going to look something like this. I missed barely, but that's okay, right? Yep, so this is the graph of absolute value of x minus 2. Right. And for contrast, down here, I'm going to graph its derivative. To be clear, this is f prime of x. No, sorry, f of x. It's not the derivative. That's the original function. Right. And then I'll just copy down what I have up here. There's a hole here, and this is just y equals 1. This is y equals negative 1. Let's make that a little clearer. Right. But at 0, oh, I'm sorry. oops. Oh, I'm sorry. That's the wrong one. That's what we graphed earlier. Shoot. We have to shift this, right? It's shifted over here now. This is going to be y equals 1, and then this will be y equals negative 1. All right, that's better. Okay, so what we're seeing here is this. When you look, when x is greater than 2, this is just the straight line y equals x minus 2. In other words, its slope is 1. So when you look at the slope at any of these points on the line, the slope will be 1, right? So m is 1 here. That's 1. When you look to the left, when x is less than 2, this is the graph of y equals negative x plus 2. So here we have a slope of negative 1. And as you can see, the y values of the derivative, right? So this is the graph of f prime of x. It's going to be negative 1 for any x less than 2. But the original question was, what is the derivative at 2 itself? So at 2, where are we? We're right here at this little corner. So what's the tangent line at that corner? Right? What's the slope of the tangent line at that corner? Is it 1? Well, if you look a little bit to the right, sure, it's 1. But if you look a little bit to the left, it jumps to negative 1, right? There's this big jump here, right? It's not a nice smooth curve here, right? The function doesn't jump, right? But the derivative does. And so at x equals 2, there is no derivative. Right? You can't jump from negative 1 to positive 1, you know, all at once at x equals 2 itself, right? Okay, so yeah, so for a graph, if a graph comes to a corner like this, right, or a cusp like this, at that point, there will be no derivative there, right? It'll be non-differentiable. Okay, but everywhere else it is differentiable, and the derivative for this function here, it's either 1 or negative 1, depending on whether x is bigger or less than 2, right? Yeah, this was the original function we graphed here, right? So, yeah, right, now notice that that's a different question from, is this continuous, right? So this function f is continuous at 2, but not differentiable at 2. Okay, so you can be continuous but not differentiable. And in terms of the graph, that usually means that it comes to a corner like this or a cusp. You can say a cusp or a corner. So when the graph comes to a corner, it could be continuous, but it's not differentiable. There's no derivative at that point because there's no tangent line at that point. Right? Right. Remember, a tangent line implies that the graph is smooth. So when the graph is smooth, right, well, smooth in quotes here, that means that the function is differentiable. So in other words, if the original graph looked like this, there's no corner here, right? This is smooth now. So that means the derivative will be positive here and negative here, right? Because the slope is positive here, and then the slope will be negative, oops, tangent line, right? Slope will be negative here. And right at the bottom here, right at the bottom, the slope will be 0. Right? So we'll see this a little later on, that when you have something like this or something like this, either a peak or a valley, right? At the peak, the tangent line will be horizontal. So the derivative will be 0 there. But that also happens for a valley, right? At this bottom point here, the slope will be 0, so the derivative will be 0 here as well. So one additional use for derivatives is finding the maximum or the minimum at a specific, maximum or minimum of a function, right? So that's going to come way later, but that's a preview. And yeah, so remember, differentiable just means the derivative exists and it's some number. Not differentiable means that this limit here does not exist and it does not have a derivative. Right? Even though the function might exist there, the derivative might not. Okay, so again, a long video. We covered a lot, but this is what you need for derivatives, and it's just the idea of the derivative. What does the derivative represent, right, in terms of the graph, the tangent line, and in terms of position, right, it represents the instantaneous rate of change or the velocity. And yeah, and mostly just finding the derivative using the limit definition. And I know those can be pretty tedious. And there's a few for homework. There might be, 4 or 5 of them that you want to do for homework. Some of them should be easy. Some of them might involve a lot of algebra. But you should try as many of those as you can. So I hope that helps.